Hello, welcome back to our discussion on the energetics of nuclear reaction. Earlier, we discussed the idea that fission and fusion both leads to a more stable nuclei. In fusion, the lighter nuclei combine to form a heavier product, moving up towards the maximum in the nuclear binding energy plot. If you recall the graph that illustrate here, when the plot of nuclear binding energy per nucleon versus the mass number, as the mass number increases, the nuclear binding energy increases. However, there is a point that it will start to decline, and this is the maximum, the area where the nuclear binding energy is maximum. Then we presume that this is the area of stability. Okay, so moving on, for a larger nuclei can split to a lighter nuclei to attain to reach this area of stability to move up. Okay, whereas for a lighter nuclei, they can combine to form a nuclei that which belongs to the area of stability here in this graph. Okay, and when again we define the previous discussion of types of nuclear reaction, when a larger nuclei is split up, that is nuclear fission, and when two lighter nuclei combine, that is a fusion. Okay, so moving on the discussion, first we have the nuclear fission. Nuclear fission is a nuclear reaction in which a heavy nucleus is split into lighter nucleus, liberating huge amount of energy. The amount of energy is a result of the conversion of the mass to energy that occurs during exothermic reaction. The relationship between the mass and the amount of energy formed can be also calculated via the Einstein equation, where energy is equal to mass times the square of the speed of light. We can therefore relate the amount of energy liberated by a nuclear reaction involved in a nuclear fission or fusion is equal to the mass defect times the speed of light square. So where the delta M is the mass defect, which is expressed as the difference between the sum of the mass of the product minus the sum of the masses of the reactant side. Okay, to illustrate that, let us have an example. For the first example, let us calculate the energy released by a nucleus of uranium-235 if it is split into barium-141 nucleus and a krypton-92 nucleus, according to the given equation. That uranium-235, when bombarded by a neutron, okay, this is the transition nuclei, which is not stable and later will be split into barium 141 and krypton 92 and 3 neutron particle. Okay. Given the mass of the atoms for uranium-235 as 235.0439239 atomic mass unit, and barium-141 atomic mass of 140.9144064 atomic mass unit, and krypton-92, the atomic mass is 91.9261528 atomic mass unit. And for the mass of the neutron particle, it is 1.008665 atomic mass unit. Okay, for the first step, we compute for the mass defect by taking the sum of the mass of the product minus the sum of the mass of the reactant. So for this equation, where uranium is splitting to barium 141 and krypton 92 by the bombardment of its nucleus. In the product side, we have barium 141 and krypton 92 plus 3 neutron particle. Okay, so we take the sum of the masses of this product minus the sum of the masses in the reactant, that is the mass of uranium-235 and a mass of 1 neutron. So if we plug in the values as given, the mass of barium 141 is 140.91444064 plus the mass of krypton 92, 91.926158, and 3 times the mass of a neutron, 1.008665 atomic mass unit. That's for the product. For the reactant, we have the mass for uranium-235, 235.0439239, and a mass of 1 neutron is 1.008665, and the sum in atomic mass unit. So the product would have a sum of 235.8665542 atomic mass unit, and the reactant, the sum of the reactant is 236.0525889 atomic mass unit. So the difference is negative. That means this is an exothermic. Okay. The fission reaction is an exothermic, and that is the energy that is used in some nuclear plant. Okay, so it's negative 0.1860347 atomic mass unit per nucleus of uranium-235. Now you may ask, why is it the binding energy is positive? Because that is the energy required to hold the nucleons in the nuclide of an isotope. But if you break that nucleus into its nucleons, that is the energy release. So when you break the nucleus of a carbon-14 in the previous discussion, that is the energy that will require to light up a 100-watt light bulb for more than 3,000 years. Okay. The binding energy of 1 mole of carbon-14. Likewise, in the previous discussion, we compute how many times we can go around the Earth equator using the binding energy that can be released by 1 mole of lithium-7. Okay. By comparing that with a thermochemical energy released by burning gasoline using our ordinary car. Okay, moving on to this discussion, we convert that mass defect to energy by using the Einstein formula. That energy, the mass is converted to energy by the Einstein formula, that is delta E is equal to mass defect times C squared. So we plug in this value, like we convert the atomic mass unit to kilogram per nucleus of uranium-235, and we multiply it with the square of the speed of light. Okay. And we obtain that the energy that can be released per nucleus of uranium when it undergo a fission to barium 141 and krypton 92 is negative 2.7764 times 10 to the negative 11 joule per nucleus. That is per nucleus of uranium. So if we are asked further, what mass of octane C8H18 would have to undergo combustion to provide the same quantity of energy as that has released by the fission of 1 kilogram of uranium to produce barium 141 and krypton 92. Okay. So to do that, we let us convert first this energy per nucleus of uranium 235 to energy per kilogram, energy released per kilogram of uranium 235. Okay, we have convert that negative 2.7764 times 10 to the negative 11 joules per nucleus. And since for every nucleus you have one atom, and for every mole you have 6.02 times 10 to the 23rd atoms per every mole. The unit here, atom, atom cancel out. The nucleus, nucleus cancel out. Okay, the mole, mole cancel out. And what is left is the gram is converted to kilogram. Okay, this is the isotopic mass of uranium-235, which is given in the problem here a while ago. Okay, so computing for that, that will give us negative 7.1134 times 10 to the positive 13 joule per kilogram of uranium-235. So this is the energy released by the fission of 1 kilogram of uranium-235 to produce barium 141 and krypton 92, and of course plus 3 neutron particle. Okay, to continue, to solve for the mass of octane that will produce this much of heat release. Okay, to continue, to compute for the mass of octane that would have to undergo combustion to provide the same quantity of energy as released by 1 kilogram by the fission of 1 kilogram of uranium-235. We repair again to your module on fuels. Okay, from page 10, module on fuels. You have for octane, here, the energy density is equal to negative 33,433. That means it is exothermic. The unit is megajoule per cubic meter. And density of octane is 698, that is kilogram per cubic meter. Okay, here. Okay, so to get the mass of octane that needed to burn or to undergo combustion, we have be equal to this energy, negative 7.134 times 10 to the 13 joule per kilogram of uranium-235. Then we have negative 33,433 times 10 to the 6. The prefix capital M is mega. That is 10 to the 6 joule per cubic meter. Okay, we're asked for the mass. So the joule cancel out. Then using the density, since we have 698 kilogram per cubic meter, the cubic meter will cancel out. That will give you kilogram of octane. So we have the value will give you 1,485,000 octane. So if you express that in metric tons, you have 1,000 kilogram per 1 ton. So we can divide that by 1,000. So that is 1,485 tons of octane. Okay, that is the mass of octane needed to combust to equate the energy of 1 mole uranium-235. Okay. See, because in our discussion on thermochemistry, we have only, again, you can recall that the energy released in an exothermic chemical reaction is typically on the order of hundreds of kilojoule per mole. So you need 1,485 tons of octane to be burned to equate that much of energy released by 1 kilogram of uranium-235 undergoing fission reaction in splitting into barium-141 and krypton-92. And since that nuclear fission is a chain reaction, for every 1 neutron that will bombard the nucleus of uranium-235, 3 neutrons is part of the product. So this neutron as product of nuclear fission will be used up for the next nuclei of the uranium-235. So the amount of energy that can be related during nuclear fissions of uranium-235 is uncontrollable, and it gives you enormous amount of energy. Okay, moving on. Okay, we have for number 2, the first nuclear transformation discovered by Rutherford can be represented by the shorthand notation nitrogen-14 that is bombarded by an alpha will produce oxygen-17 and a proton. You are asked to write the corresponding nuclear equation for this process. And likewise, you are asked to calculate the energy change of this reaction in kilojoule per mole. Okay, the respective atomic masses are given for nitrogen-14. It is 14.00307 atomic mass unit. For the alpha particle or helium atom, it is 4.00260 atomic mass unit. And for proton or hydrogen atom, that is 1.0072825 atomic mass unit. And for oxygen 17, it is 16.99913 atomic mass unit. Okay. Okay. For letter A, we're asked to write the corresponding nuclear reaction. Okay, we have nitrogen 14, okay, plus an alpha, which is can be represented by helium atom, and the product is oxygen 17 plus a proton, okay, by the hydrogen atom. So this is the nuclear equation for the shorthand notation. Then we check if it's balanced. 7 plus 2, 9. 8 plus 1, 9. 14 plus 4, 18. 17 plus 1 is 18. Then the next problem is we're asked to calculate the energy change for this reaction. Since the energy change is the mass defect, C square, so we solve for the mass defect, which is the sum total of the mass of the products minus the sum total of the masses of the reactants or reactants. Okay, we have here the product and that's the reactant, so the mass of the masses in the reactant involved is the mass of oxygen 17 plus the mass of proton minus the mass of nitrogen 14 plus the mass of alpha or helium. Okay, so if we plug in the values from the given, the mass of oxygen 17 is 16.99913 plus the mass of a proton 1.007825 atomic mass unit minus the mass of nitrogen 14.00307 plus the mass of helium or alpha particle, which is 4.00260 atomic mass unit. Okay. So the mass defect times 10 to the negative 3 AMU, and that is per nucleus of nitrogen 14. So if we convert that to kilogram, 1 AMU is 1.66054 times 10 to the negative 27 kilogram. Then you will cancel out, therefore the mass defect in kilogram, that is 2.134 times 10 to the negative 30, that is kilogram per nucleus of nitrogen 14. Okay. So next step is we calculate the energy release or absorbed. Since it is positive, the mass effect, this is endothermic reaction. Is delta the mass defect C squared. So we have 2.34 times 10 to the negative 30 kilogram per nucleus of nitrogen 14. We have 2.99792 times 10 to the 8 meter per second, and that is squared. One point 918 times 10 to the negative 15. That is joule per nucleus of nitrogen 14. Whereas for the unit of kilojoule per mole, so we can convert this to using the Avogadro's number is 6.022 times 10 to the 23rd nucleus of nitrogen 14, because per one nucleus there is one nucleus in per one atom per mole of nitrogen 14. Show delta E, the change in the energy is 1.155 times 10 to the positive 11 joule per mole nitrogen 14. Since we are asked in the unit of kilojoule, so that is 1.155 times 10 to the 8 kilojoule per mole. The positive sign for the mass defect would mean the process is endothermic. Transformation of nitrogen 14 to oxygen 17 by bombarding the nuclei of nitrogen 14 with alpha particle, producing oxygen 17 and emitting a proton particle as well in the reactant. Proton particle in the product. So we have here translocation, and the two particle involved is an alpha in the reactant and proton in the product. Okay, for the third example, we have the major reaction taking place during hydrogen fusion in a young star is 4 moles of proton would give you a mole of helium, 2 positron particle, and 2 gamma particle and energy. The reaction that energy is on the product side would indicate that this reaction is exothermic. Okay. How much energy in mega electron volt is released per helium nucleus formed and per mole of helium, given the masses of a proton or an hydrogen atom is 1.007825 atomic mass unit, and for helium atom 4.00260 atomic mass unit, and for positron it is 5.48580 times 10 to the negative 4 atomic mass unit. Okay, for our solution, we'll not use the equation of Einstein that convert the mass defect into energy using the mass defect C squared, because the unit required here is mega electron volt, so we can just convert directly the mass defect to electron volt conversion. Okay, so moving on, we compute for the mass defect. which is the sum total of the masses, the products, minus the sum total of the masses of the reactant. We have only one reactant here. So that would give us the mass of helium plus 2 times the mass of a positron. The gamma has no mass, no charge, minus 4 times the mass of a proton. So we substitute the values. For helium, we have 4.00260 atomic mass unit plus 2 times the mass of a positron, which is 5.4858 times 10 to the negative 4 atomic mass unit, minus 4 times the mass of a proton, 1.007825 atomic mass unit. So the mass defect, if we compute that value, will give us negative 0.027603 atomic mass unit per helium nucleus. Okay. So the next step is we convert that mass defect into energy by converting it to mega electron volt. The negative 0.027603 AMU per helium nucleus is 931.5 mega electron volt per atomic mass unit. So that will cancel out. So the energy is negative 25.71 mega electron volt per helium nucleus. Okay. Then you are likewise asked to express this per mole. So the energy released is negative 25.71 mega electron volt per helium nucleus using the Avogadro's number 6.022 times 10 to the 23rd nucleus, which is 1 nucleus per atom, and that is per mole of helium. Okay. So the energy release is 1.548 times 10 to the 25. This is cancelled out. mega electron volt per mole helium. Okay. Okay, that's all for the energetics of nuclear reaction involving nuclear fission and fusion. Okay, in the next episode, we're going to discuss the rate of radioactive decay. Okay, see you then on the succeeding episode, which will discuss on the rate of radioactive decay.